We've talked about mathematical induction in class, and it's this, if I think about it in terms of rules of inference, it's this idea that if I have a propositional function that takes natural numbers and it gives me a truth value, if p of 0 is true, and for all n, p of n being true implies p of n plus 1 is true, therefore I can verify that for all values of n, p of n is true. Talked a little bit of why this works. The idea is that the p of 0 being true is kind of like getting on the first rung of a ladder. And then this second statement is saying, well, if I'm on some rung of a ladder, I can get to the next one. And really, that's all that's happening. But if I want to start essentially verifying each element of the sequence p of n, we can actually do that using formal proof using rules of inference. So using regular step reason format, I can see that p of 0 is a premise, and for all n, p of n implies p of n plus 1 is a premise. And essentially, I want to conclude this. Well, I won't be able to conclude this using our proof now, but what I'm going to do instead is I'm going to step through and show you that lots of these values are going to be true. And the reason I need to do this, I need to use universal instantiation. So for instance, I can say, well, p of 0 implies p of 1 by universal instantiation. And if p of 0 is true and p of 0 implies p of 1, by modus ponens, we have p of 1. So modus ponens give me that p of 1 is true, and I can instantiate again to say that p of 1 implies p of 2. So I see that I can use universal instantiation of, again, this universal quantifier to put in n equals 1, and see that p of 1 implies p of 2. And therefore, since p of 1 is true and p of 1 implies p of 2 is true. And I can continue on this ad nauseum. So we see that we can just keep on going, follow this pattern over and over again, and I will complete a proof for every finite n. I will have a proof that p of n is true. However, I can't write down the full proof because p of n can be any arbitrarily far value. It could be larger than the number of atoms in the universe. I will never finish writing the proof. But you can believe me that if I were given an arbitrary number of steps, I could get there eventually. This idea will work. The other way to think about it is, suppose I was proving by contradiction. Suppose I was trying to show the opposite of this statement. The opposite of the statement would be there exists a value n such that p of n is false. And here's where the crucial idea would be, is that I would try to let n be the minimum value where p of n is false. If I let n be the minimum value where p of n is false, I know that n is not 0 because p of 0 is true. But then, it must be that n minus 1, I can plug into the propositional function and get a true value. P of n minus 1 is true, my n being the minimum where it's false, but I also have that p of n minus 1 implies p of n by using universal instantiation again. That means that p of n is going to be true, which is a contradiction to my assumption that there exists a minimum value where I'm false. Therefore, no matter what, we're going to be good. And this idea that I have a minimum value where it's false is a very, very subtle fact that I can actually do this. It's called the well-ordered property of the natural numbers. That's where everything works out.